Okay, so in this relatively short segment, I'm just going to go through this corollary of the previous theorem we proved, right? Which, as I said before, that theorem, which was, theorem 21.4, is a generalization of 18 point, let's see, I believe it was 18.1 and 19.2, yeah. So 18.1, 19.2, right? And so this corollary kind of makes that even more clear, right? Because remember, in the statement of theorem 21.4, we were dealing with functions from one metric space to another metric space, where both spaces were just completely abstract, right? But if we make the codomain be a set of real numbers, right, or the set of real numbers, then we can use some of what we know about the real numbers to translate the statement of theorem 21.4 into a more familiar form. So this is corollary 21.5. Let f s to r be continuous, where S is just an arbitrary metric space, and R, of course, has the Euclidean metric as usual. I'm going to probably stop writing this at some point because it's the default. So, and let E be a compact subset of S. So then, right, remember in the first part of the general theorem, we said that f of E is compact. But in this case, what we're going to say is f of E, well, okay, yeah, we'll say f is bounded on E. There's actually a bit more you could say, but this is what we're primarily concerned with here. And then, of course, f achieves a maximal, and a minimal value on E. So proof is very short. We know f of E is compact, meaning it's closed and bounded by the Heine-Borel theorem. Right. So then the boundedness gives us part one immediately, right? If f of E is bounded, then clearly f itself is bounded. That's almost just by definition. So for part two, since f of E is closed, and that's what I meant when I said there's more you can say here. I guess it's basically contained in the second part. Well, sort of. At least the important part of it is contained in the second part. F of E contains the supremum of f of E and the infimum of f of E. So f achieves these values, right? Because the supremum, if it's not in the set, then there's still a sequence of points that, well, no matter what, basically, no matter what, there's a sequence of points in f of E that approaches the supremum of f of E. So if f of E is closed, then the supremum has to be in f of E. And similarly with the infimum. And then, of course, if they're in f of E, that means that they're achieved, right? Those values are achieved if they're in f of E. And if they're achieved, then they are the maximum and minimum values. I mean, in general, if a set contains its own supremum, then the supremum is actually a maximum, and the same thing is true for the minimum. If the set contains the infimum is actually the minimum. So this means that supremum of f of e and infimum of f of e are the maximum and minimum of f of e, you know, respectively. And of course, then the fact that they're in the set means that they are also achieved. So that's the corollary. I mean, that's basically it. One thing I'll say, which is sort of part of what they talk about in, you know, examples 4 and 5, I guess, which I'm not really going to go through, but you know, so one thing, I don't know, example, you know, for a curve or a path, in RK, right? We know the curve gamma of AB, right? The entire image, the image of the entire interval AB is some curve in RK, right? This curve has to be closed and bounded. Closed and bounded, right? So, I mean, this isn't actually, okay, this is sort of not actually a consequence of this, you know, of this corollary specifically, because for a curve, right, or for a path, this is not a real valued function because the values are actually in RK. But of course, the Heine-Borel theorem applies to RK anyway. So this is by analogy with corollary 24 or 21.5. Okay, so you could basically make the same statements for a path, even though the codomain is not R, right, which is what we were assuming over here. Even though the codomain is not R, you can still say the same things. And that's a useful thing to be able to say. And of course, another thing you could say is that, well, I mean, obviously, you know, the absolute, or sort of the magnitude, I guess, if you want to think about it as, you know, the distance from gamma of t 0, which is like, you know, well, whatever. Never mind. It's not worth, it's not a very good example. Well, anyway, yeah, I think that does it for this video. I don't think there's a lot more that's worth saying in the time we have, unfortunately. But I mean, I do recommend that you look at the examples in the book. I think they are helpful. It's just I don't think that they would be very useful for me to go through in lecture when there are other things that it might be better to talk about. So anyway, I'm actually going to, so now after this, we're going to skip the stuff about the Baire category theorem and everything. So this is it for section 21. And then I'm actually going to include the stuff that I wanted to cover from section 22. I'm going to combine with this lecture. So there will be a bit of a change in the lecture schedule because of this. And I think because I didn't want to cover everything in section 22. And I also don't want to cover everything in, in section 21. And I'm not going to cover everything in section 22. I'm going to cover most of section 22, but not all of it. And it's just not enough for an entire lecture on its own. So I think I'll just combine it with this, and that'll give us more time for some of the more substantial lectures in the future. So.